2 videos ago, I showed you a case where the normal force and the weight was equal. That was the old coffee cup sitting there on your kitchen table, minding its own business, steaming a little bit. Last video, I showed you a case where the weight and the normal force were not equal. That's the case when you're on an elevator that is accelerating, either up or down. Whether it's accelerating upward or accelerating downward makes no difference. In both cases, the normal force and the weight are not the same. Here's another case where the normal force is not the same as the weight. In fact, it's not just another case, it's a suitcase. So, we're dragging a suitcase across the floor of the airport, okay? And it's just moving along the floor. We're not picking it up. We're pulling it with a force of 25 newtons. So if the force is 25 newtons, we're pulling on it here. Let's say that makes an angle of 30 degrees relative to the horizontal, relative to the positive x-axis. So if theta is 30 degrees, we're pulling up with a force of 25 newtons. So we know our force. Okay. 2 questions. What's the acceleration of the suitcase? And what is the normal force? Hint, hint, it is not equal to the weight. The mass is 15 kilograms of the suitcase, so the weight to within 2 significant figures is 150 newtons. Okay, not that heavy of a suitcase, actually. That's like, you know, a 30 to 40 pound suitcase, something like that. So it's small enough to where you get where they won't go over the 50-pound thing where you got to pay more. So it's all good. Suitcase dragging across the floor of Hartsfield, and we want to know what the acceleration is. Right, the acceleration is obviously going to be in the x direction. All right, we have our standard reference frame up here. And in order to define these 2 things, acceleration and the normal force, the first thing we're going to do is what? Number 1, first thing, out of the get-go, we're going to make a free body diagram. And sometimes it's okay to draw the free body diagram on the actual drawing, sort of the physical picture. Sometimes I think it's easier to draw a free body diagram separate. In this case, I want to make it separate. Doesn't really matter, you can do it either way, but I think it's less clutter just to draw a free body diagram separate from the physical picture of the suitcase, of whatever the object happens to be. So we know there's a force up and to the right. We know this angle here, 30 degrees. What other forces act on this suitcase? What's one force that always acts on all suitcases unless they're orbiting Saturn? Actually, in that case, this force is still acting on it. Gravity, right? Weight. There's going to be a weight down. There's going to be the weight vector down. Magnitude mg, negative direction. And then there's going to be the force of the floor up on the suitcase. Right? It's not falling down through the floor is supporting it. It's going to feel a contact force, a normal force from the floor. Oh, by the way, I meant to mention to you before, let me go ahead and draw this here. The word normal in this context is not to be contrasted with weird, or oddball or bizarre, okay? The word normal simply means perpendicular. It's a math word. Means perpendicular. Perpendicular to the surface, in this case the floor. The normal force always is perpendicular to the surface we're talking about, the contact surface. And in this case, the suitcase is in contact with the floor, which is here. So the normal force is perpendicular to the floor, which is up. Okay. Those are our forces. That's it. Those are all our forces. Okay. So we've drawn our free body diagram, but your free body diagram is not really finished yet. We've included all the forces. They're all there. Nothing more to add. No more forces acting on the suitcase. But because we're going to have to apply Newton's second law in X and Y, we have to resolve this force vector F into its components, just as we did before. There's going to be an X force here, F sub X, and there's going to be a Y force here. We're pulling up and to the right, so there's going to be a component up and a component to the right. F sub Y is the component up, F sub X is the component to the right. Okay? And F sub X, as per usual, is hypotenuse F times cosine of theta. F sub Y is hypotenuse F times sine of theta. Force vector F is up and to the right, therefore we're going to have a component up, Fy, and a component to the right, Fx. And it is these components that we are going to be using when we sum forces using Newton's second law. So remember, first step, draw a free body diagram. Second step, apply Newton's second law. And it's not clear how these are going to come out of Newton's second law. This is not like back when we had the projectile motion equations, where you could look at an equation and see the thing you're looking for and then solve for it. F equals ma does not include a normal force, but it will. Once you apply this particular situation, or rather once you apply Newton's second law to this case, the things we're looking for will show up in our equations. You have to make the equation using Newton's second law. You're not given the equation. That's a big difference between chapter 4 and chapter 5. In chapter 5, you've got to come up with the equation yourself by applying Newton's second law and then solve it for the thing you're looking for. So let's solve it. F sub x equals m a sub x. So we're going to look at all the forces in the x direction, add them up, okay, and then set them equal to max. What are all the forces in the x direction? Let's look at our free body diagram, because this tells you how to unpack your sum of forces. Unpack the left-hand side of this thing here. This diagram tells you how to do it. Look in the x direction. There's only one force in the x direction. There's only one, friends, and that is F cosine of theta. All other vectors point in the y or negative y directions. That's it. That equals ma. And again, I'm dropping the subscript on the a because I told you from the get-go that the suitcase is moving in the x direction. It's not being lifted up. Okay, this force is not enough to lift it up. So I'm telling you it's moving all in the x direction. So we can drop the subscript because a is equal to a sub x. And we can solve this for a. So a is F cosine theta divided by m. F is 25. Cosine 30 over the mass, which is 15 kilograms. You do this, and you will get A is 1.4 meters per second squared. So we can write that the vector A is 1.4 meters per second squared in the x direction. So A is 1.4 meters per second squared in the x direction. That's it. That's your acceleration. And notice that came out of applying Newton's second law in the x direction. Now, let's apply it in the y direction. See if we can get the normal force. We will. Some of the forces in the y direction is MAY. So now we need to fill out. We need to look at what all the forces are in the y direction. Again, your free body diagram here, your free body diagram will give you everything you need. If you learn how to read it, you can read it right off like a book. Super awesome. We have 2 positive forces and 1 negative force. Let's write them down. We're going to have Fy, which is F sine of theta. That's the pink force up, right? That's positive, plus the normal force, which is also positive, minus the weight. That is the sum of all the forces. You take the forces and you add them up. They're not all positive. Some are negative, like the weight here. But still, you're adding them all up. You got 2 positives and a negative, and you're adding them all up. That's what sum of forces means. But what is AY equal to? Zero. It's not moving up or down. It's moving across the floor. There is no acceleration up or down. Again, I told you at the get-go, it's moving to the right in the positive x direction. It's not accelerating up or down, so that's simply equal to 0. So now we can solve this for n. So F sine theta plus n minus W equals my favorite number, 0. So the normal force is weight minus F sine theta. The weight, if you use all the significant figures, if you use all the figures, it's actually 147.15. Okay. I rounded it to 150 here, but you use all the significant figures until the end, so I went ahead and put all of them in there. Minus, what was the force? 25 newtons times sine of 30. When you do all this, you get the normal force is 130 newtons. In fact, the normal force with a bar over it, the vector is 130 newtons in the positive y direction. So normal force is 130 newtons, the positive y direction. Right there it is. Notice from this, the normal force is not equal to the weight. It is less than the weight in this case because you're helping out the suitcase by giving it a bit of a lift. So the floor is not responsible for holding it all up. You're helping out the floor, so the actual contact force between the floor and the suitcase is less than the full weight of the suitcase. Because by pulling it up a little bit, you're giving the suitcase some lift and making the contact force with the floor a little bit less. It is less than the weight. 130 newtons for the normal force, 20 newtons more is the weight. Not equal. Okay, big picture. Free body diagram. First step. Second step. Newton's second law. Third step. Solve for quantity of interest. It's a 3-step process we take. Free body diagram, Newton's second law, and then algebraically solving for the quantity of interest. We will keep our eyes on these 3 steps in the next video and in several videos to follow. As a general sort of approach to solving these problems in chapters 5 and 6. All right, that's it. Have yourself a good afternoon, whatever part of the day it happens to be. And I'll see you later when we're going to talk about, next step is going to be what? Oh yeah, inclined planes. Prepare yourselves. It's going to be awesome.